Welcome back to the Deep Dive. Today we are taking the most ambitious trip possible, a journey right into the future of space travel. We've got a massive stack of sources today comparing two completely different philosophies on how humanity might actually conquer the cosmos. Our mission is to really get our heads around the two major constraints that have defined all of spacecraft propulsion since we started launching things. First, you have to expel mass to create thrust. That's just Newton's third law, no getting around it. And second, if you want to move fast, you run smack into inertia, the crushing g-forces that limit, any kind of maneuverability and speed for a crewed vehicle.
And we have two incredible blueprints for getting around those constraints. One document, Project Impulse, is just a masterpiece of engineering. It accepts the laws of physics as they are and just aims to push what we can do to its absolute adaptive maximum using AI and recursive design. The other, the Quick Q Drive, is theoretical physics at its most speculative. It's basically asking, instead of building a better rocket, can we find a cosmic cheat code?
A cheat code?
By hacking the fundamental nature of space-time itself to circumvent the speed barrier entirely.
That is quite the contrast. So we're comparing what the ultimate expression of human ingenuity and iteration, a kind of self-improving robotic dancer,
Right.
to a genuine physics wildcard.
Right.
Given that, let's ground ourselves first. We need to know what the peak of classical engineering looks like before we jump into theoretical metaphysics.
Precisely. And Project Impulse starts with a brilliant premise. It avoids any reliance on, quote, unproven theoretical breakthroughs. So no warp drives, no reactionless drives. It argues that by just combining established physics with machine learning and automated self-correcting design, we can achieve what otherwise looks like pure science fiction.
And that refinement, it starts with the geometry. They decided the whole traditional rocket shape is inherently inefficient for high-velocity, multi-axis maneuverability.
Correct. The core solution is architectural, a dual-layer spherical spacecraft. The idea is radical, but also kind of simple.
A sphere, okay.
The outer sphere is the pure propulsion shell. It's absolutely covered in these distributed microemitters that can expel particles in any direction.
So the thrust is totally omnidirectional.
Exactly. The inner sphere, though, is where the crew and the critical systems are, and it is completely isolated from that outer shell.
Oh.
By a buffer gap. It's precisely maintained between about 0.5 meter and 1 meter. The entire architecture is designed to manage force, not just produce it.
Okay, so that structural separation is step one, but how do they actually solve the inertia problem? I mean, rapid acceleration is still rapid acceleration. If that outer shell thrusts hard, the inner shell should feel it just as badly.
Right, and that's where the inertial damping system comes in. The inner sphere isn't just passively floating in there, it's being actively stabilized.
Ah.
Using localized, phase-controlled counter impulses. You can think of it like an incredibly advanced predictive movement controller.
So it's that impulse-based noise canceling for motion they mentioned, like it hears the g-force coming and cancels it out.
That's the perfect analogy.
Yeah.
But it's more complex than just canceling a vibration.
Yeah.
It operates using what they call temporal and spatial lead. So when the outer shell initiates a major burn, the system calculates the precise inertial forces that will hit the inner sphere nanoseconds later.
Okay.
And the inner sphere then generates precise opposing counterforces in that buffer gap before the main acceleration wave even arrives.
So it's predictive. It anticipates the jolt and cushions it before it happens.
Exactly.
Yeah.
That predictive mechanism, that temporal lead, lets the system constantly shape the overall load, basically spreading a massive sudden g-force spike across a slightly longer time frame.
And that load modulation is what reduces the g-force on the occupants.
Dramatically. All while, and this is key, strictly respecting conservation of momentum. No magic here.
That is the sort of complexity that only an AI could manage in real time. And the intelligence is also focused on efficiency, right? Energy recapture. The system isn't just moving, it's learning how to move.
Exactly. The AI-guided efficiency matrix learns the optimal emission profiles. So, does the situation call for a narrow high-velocity beam or a broad diffuse sheet of particles? It's always maximizing efficiency. But the real genius is what they call the recuperative feedback loops.
Okay, that sounds like they're trying to get around the second law of thermodynamics. Can you really capture energy from an emission event?
Not perfectly, of course not. But you can capture the useful byproduct energy. When the two skiers interact, the outer one pushing, the inner one counter-pushing, they generate these really complex, overlapping vector fields.
Metawave patterns, they called them.
Controlled metawave patterns. And the system harvests the resulting harmonics, the localized pressure nodes or field overlaps. They use induction systems, piezoelectric layers, all placed within that buffer gap.
So they're turning the messy, chaotic energy of acceleration, the momentum noise, into usable electricity.
They're effectively recycling momentum noise. It's brilliant.
It's unbelievably clever. Okay, let's talk about the engineering bottleneck. The document was clear. The physics is solvable. I mean, delta P equals m times v. That's simple. But the mechanical precision and the energy density are the real hurdles. Why is precision such a limiting factor here?
Because the effectiveness of that whole damping system and the energy recapture loops, it all depends on tolerances that are currently impossible for human manufacturing to achieve on this scale.
So if your emitter array is off by just a micron,
Your metawave pattern becomes useless noise. The whole system fails. So the solution is to remove the limitations of human precision entirely.
and that's where the recursive autonomous engineering comes in, the AI maker loop.
That's the one. You have two layers working together.
Hmm.
First, the simulation intelligence layer, the SIL. That's the brains.
Okay.
It discovers viable component structures in this high-fidelity physics sandbox. It designs the perfect emitter, the perfect induction coil, you name it.
And then the second layer builds it.
Right. The maker interface layer, the MIL. That's the hardware. It fabricates the parts. But here's the critical distinction. The AI doesn't just design parts for the spacecraft. It designs parts to upgrade the maker itself.
Wait, what? So the AI is continuously evolving the fabrication hardware. It designs a new, higher precision extruder head, prints it, installs it.
And then uses that better tool to print the next generation of spacecraft components.
That's self-amplifying engineering.
Exactly. The system starts with a certain capability, but the AI's objective is just continuous improvement of its own toolset. This completely eliminates the constraint of human-defined manufacturing limits. The whole project evolves at machine speed toward perfection. It's not marked by one single breakthrough component, but by this emergent behavior, a learned choreography of impulses that's constantly adapting its own physical systems.
That sets a breathtaking ceiling for what's possible under current physics. So if Project Impulse is the ultimate expression of iterative classical engineering, what happens when we just abandon that framework completely?
Then we pivot sharply. We go to the theoretical frontier, the QAQ drive.
Yeah.
While Impulse tries to maximize efficiency within known constraints, QuickQ wants to rewrite the constraints themselves. And this model is purely speculative, coming from the School of Digital Physics.
And its core concept is about the very nature of spacetime.
It is. The QuakeQ concept interprets spacetime not as a smooth, continuous fabric, but as an emergent phenomenon. Meaning it arises from a discrete quantum computational substrate at the Planck scale. You can think of it as the ultimate pixel size of the universe, incredibly tiny, about 10 to the minus 35 meters.
So if the universe is basically running on a massive computational system, what happens when you start moving really, really fast?
And what's so fascinating here is the reinterpretation of relativity. All those classical relativistic effects, mass increase, length contraction, they're seen not as fundamental limits, but as a velocity-dependent degradation of spacetime's rendering resolution.
Rendering resolution, like a video game.
Exactly like a video game. They call it left duck. When you move slowly, the resolution is perfect. But as your velocity approaches the speed of light, as Vire goes to 2 the universe has to, well, drop the graphics quality.
So that affected resolution approaches the absolute limit of the Planck scale, zero resolution.
Pretty much.
That is a powerful analogy. It implies the speed of light isn't a hard limit, but just the point where the computational substrate runs out of processing power to render continuous motion.
Yeah.
So how does that let you travel faster than light?
To an idea called quantum hopping. When the resolution hits that Planck minimum, they define it with a transition parameter. Tuckeye, approaching one continuous acceleration, just stops. Motion transitions to discrete quantum hops between adjacent Planck scale states in that computational substrate.
And this is where it breaks from classical relativity, because under Einstein, the energy you need to reach co goes to infinity. It's impossible.
Exactly. But in the QAQ model, the energy cost per hop, the E-jump day, it plateaus at a massive but finite value. Finite. Since you're not accelerating continuously against resistance, but you're forcing a state transition, that classical energy divergence just gets circumvented.
It's like you need a certain amount of energy to kick down a door, but once it's open, you can step through. What's that energy cost? Is it manageable?
It is still astronomical,
Well,
close to the Planck energy scale, so about 1.23 times 10 to the 19 GeV-AP. We are nowhere near harnessing that kind of energy. But the philosophical breakthrough is that the cost is finite. FTL becomes theoretically possible, not physically precluded.
So if we could somehow find that activation energy, how would the Quake drive actually work?
You would have to force the spacecraft into that quantum hopping regime where psi is about 1, and then, this is the key part, induce controlled quantum jumps. The theorists suggest using engineered space-time curvature to guide the hops and achieve effective FTL.
And this is different from other warp drive concepts like the Alcubierre drive.
Massively different. The Alcubierre drive needs negative mass or exotic matter to create a warp bubble. Because the Quake-Q drive uses the discreteness of space-time to get around the energy problem, its warp effect doesn't require those unstable negative energy densities.
It uses the finite jump energy to make shortcuts.
Essentially, yes.
Now, let's be very clear about the status of this model. The sources were refreshingly honest about its limitations. They included a simulated peer review that was skeptical.
That was a great moment of self-critique, yeah.
Yeah.
They admitted finding and correcting an initial dimensional error in their own E-jump equation, which shows you how sensitive this is. The simulated review gave it a high score for originality, mostly because it's pulling from digital physics concepts that a lot of people ignore.
But the plausibility score was devastatingly low, less than 10%. Why was the feedback so harsh?
For the most basic reasons in physics. 1, a total lack of empirical support. And 2, the immense risk of violating causality.
Time travel paradoxes.
Exactly. If you're hopping across space-time states, maintaining local Lorentz invariants, the idea that the laws of physics are the same for everyone becomes nearly impossible. They admitted that engineering Planck-scale transitions is far beyond us, and this model is really just a conceptual exploration for now.
Okay, let's pull back and synthesize what we've learned here. We have two competing visions for the future of motion. Project Impulse is this: stubborn path of iteration and intelligence, all under strict physical constraints.
Right.
And the Quake drive is the speculative path, gambling on a fundamental loophole in the rules of existence itself.
The bottlenecks just highlight this dichotomy perfectly. For Impulse, the limits are pure engineering. Energy density, material precision, speed of computation. We know the rules. The challenge is just how to build it and how to power it.
But for Quake, the bottleneck is fundamental physics. It's proving that space-time is a computational substrate, and then figuring out how to control dynamics on the Planck scale. We don't even know the rules yet.
So the key takeaway for you, listening, is the sheer range of possibilities here. We don't actually need a physics revolution for massive gains in efficiency, maneuverability, and crew safety. Project Impulse shows us the power of self-amplifying engineering applied to the laws we already have.
But if the universe is computational at its deepest level, if speed limits are just resolution limits, then maybe FTL travel is just a matter of finding the right finite energy to force that quantum state transition. It's a question of whether we iterate our way across the galaxy or if we find the cosmic system password.
This deep dive has really explored two profound frontiers. One focused on the absolute maximum performance you can squeeze out of Newton's laws, and one betting on a radical change in our understanding of space-time itself.
So what does this all mean for you? Well, whether we reach the stars by designing a spacecraft that builds and evolves itself toward perfection, or by discovering a quantum trick to just skip the distance, the future of propulsion rests entirely on how much intelligence we apply to the constraints we already face.
Which brings us back to the recursive engineering of Project Impulse. If that framework proves that most of the complexity in propulsion lies in that self-optimizing control layer, that learned choreography of impulses, and not the hardware. What does that imply for other seemingly impossible engineering challenges?
So that's interesting.
Could you embed self-amplifying engineering into any complex domain, say from developing new materials to building large-scale climate modeling systems?
Right.
Could we solve problems by just letting the AI teach the system how to improve its own tools recursively? That's a challenge worth mulling over.